this video we will be looking at a very simple statistical quantity called, or statistical function called, the expectation. You are familiar with expectation as the mean or the average. Okay. So, the context is this: if you remember, we are dealing with random variables throughout. Random variables by definition will result in different outcomes. If I throw a dice right now, sometimes it will give a 1, sometimes it will give a 2, sometimes it will give a 6. So, this is obviously why it is called a random variable in the first place. Okay. So, which way the random variable actually varies, or how it gives different outcomes, is captured by what is known as the distribution. If you recall, if you have a discrete distribution such as a dice or a coin or a deck of cards, then we have something called the probability mass function that tells you how likely each one of these outcomes is. Okay. Similarly, for a continuous variable such as a height, weight, temperature, pressure, stress, strain, etc., what you have is a probability density function that tells you how likely a range of probability is, a range of values is. Okay. So, the probability that height varies between 5.6 and 5.7 is something. Okay. So, that would be a probability density function. Now, once you are given the distribution, we start using some overall ideas. It is a random variable, it has any number of large number of values, but you want to give some summary statistics. Okay. So, you want to give some qualitative and quantitative picture of what the random variable is doing, and the most common ones that we will be using, at least as far as this course is concerned, are two quantities called the expectation and the variance. Okay. The expectation is something that you are already familiar with, we usually call it the mean or the average, but in the context of random variables typically we tend to call it expectation. Okay. Now, the expectation gives the mean, average, or expected value of the random variable once you know the distribution. Okay. So, that is important, you need to know what the distribution of the random variable is, then you can find out the expectation. Okay. So, here are a couple of examples. You can say, I have invested in the stock market, what are my expected returns? Obviously, you know that the returns are not fixed, it is a random variable, but nonetheless given a certain investment, what is my expected return from the stock market? Another example is, I know that monsoon is going to hit, what is going to be the expected rainfall during the coming monsoon. Okay. So, you could ask questions of that sort. Again, this is a random variable, but overall you would still like to know what is going to be my expected crop yield, a farmer might be interested in knowing. Okay. So, here is how we define expectation. Okay. This is the average value. So, right now I am not talking about only expectation of a random variable x, but that of a function of x. So, the expectation or the expected value, both these terminologies are used, of some function x of a random variable where x is a random variable. This is the average value of f of x when x is drawn from a probability distribution P. Recall the notation, x is drawn from P is written as x tilde P. Okay. So, the denotation is, how the notation that we use is x expectation of f of x, notice the square brackets, expectation of f of x, because it is not quite a function. So, expectation of f of x given that x is drawn from P. Okay. So, this is the notation that we will be using. This is the most detailed or rigorous notation. Okay. But more often than not we use some shortcuts. If you know which probability distribution we are talking about, we simply say expectation of x given f of x. Even more simply, suppose you also know what x is, which random variable x we are considering, you can simply say expectation of f of x, and sometimes you simply say expectation of f. Okay. So, all these notations are used as far as expectation is concerned. Okay. So, mathematically how do we calculate expectation? For a discrete variable, it is simply summation of p of x f of x. Okay. And if it is a continuous variable, it is, remember now this is a probability mass function, in this case it is a probability density function, which is why you have to multiply by dx in order to get the probability. So, integral of p of x dx f of x integrated over all possible values. We will see a couple of very trivial and simple examples on the next slide. Okay. So, a generalization of expectation, which we just saw an expectation of a single variable, okay. But usually especially within machine learning we are dealing with vectors. Okay. So, this is called multivariate expectation, where basically x is now a vector consisting of x1, x2, so on and so forth up till xn. Okay. As we saw in the previous video, this could be an image, this could be temperature, pressure, velocity, etc. It could be any number of variables. Okay. So, if you have that, then you can consider each component separately, and all you will do is expectation of variable 1, expectation of variable 2, so on and so forth. The reason why I wrote it here is, notice that the variable itself, the first one is expectation over variable 1. Okay. So, if I want, let us say if my x vector is temperature, pressure, humidity, then I will take expectation over all possible values of temperature of, if you are interested in some function of temperature, so on and so forth, expectation over all possible values of pressure, function of pressure. Okay. So, that is multivariate expectation. Multivariate simply means multiple variables. Okay. X is not a single scalar, it is a vector. So, here are some trivial examples. I am going to do univariate examples here. Okay. So, all of us know, let us say you want to know the expected value of a toss of a coin for a fair coin, assuming that heads has a value 1 and tails has a value 0, then I will just do it in detail so that you get used to this kind of calculation if you are not already used to it. So, you first identify the random variable you are considering. Here the random variable is the result of the toss of the coin, and it now belongs to 0 1. Okay. What is p? You now need to know what the distribution p is. So, first identify a random variable, next calculate the probability distribution. Okay. In this case it is a mass distribution because it is a discrete random variable. Now, the probability distribution is very simple. If you have x and p of x, then x takes the value 0 with a probability half, x takes the value 1 also with a probability half. Okay. So, if you find out the expectation, it is simply 0 times half plus 1 times half, which is equal to half. Okay. All of us know this. Another way to look at it is the average value of the toss that you will obtain is basically going to be half. So, notice that the expectation, even though we have given it as the average value or the expected value, obviously you cannot say that the expected value of a cost of a coin is half, because neither heads nor tails is the actual half, it just represents an average or a weighted average of values that come out. Okay. Similarly, if you want to find out the expected value of a fair dice throw, this is going to be the average of 1, 2, 3, 4, 5, 6. Given that all of these are equally probable, assuming this is a fair dice and it is not like sort of a loaded die or something, again from the same idea you get 3.5. Okay. Let us look at a slightly more complex example. This is just to see maybe a slight increase over simple averages. Okay. So, what is the expected value of the sum of 2 dice thrown together? Now, the random variable here is any number between 2 and 12. Obviously, 1 cannot occur if you are throwing 2 dice and taking the sum. So, you have a variable that goes between 2 and 12. The probability distribution you have to be a little bit careful now. Okay. Now, notice that the probability of 2 is not the same as the probability of 3. Okay. Unlike the previous case where we had uniform probability distributions, in this case each of these probabilities is different. Okay. So, here is the distribution, both 2 and 12, if x is 2 as well as x is 12, both of these can occur in only one way, and so you for 2 you need 1 1 and for 12 you need 6 6, and that can occur in 1 by 6 multiplied by 1 by 6, which is 1 by 36. Similarly, 3 can occur in two ways, 1 comma 2, 2 comma 1. Okay. So, therefore, you get 2 by 36. Similarly, for 11, for 4 you have 3 ways, for 5 you have 4 ways, for 6 you have 5 ways, 1 5, 2 4, 3 3, okay, and 5 1 and 4 2, that put together. 7 can actually occur in 6 different ways, and so these are the probabilities. So, notice that unlike the previous examples that we took, in this case p of x is an actual non-uniform distribution. So, if you find out expectation, the same thing. So, 2 multiplied by 1 by 36, 3 multiplied by 2 by 36, so on and so forth, up till 12 multiplied by 1 by 36. If you calculate it, it comes out to be 7, okay. But the calculation is a little bit lengthy. Okay. So, the question is there an easier way of calculating this case? Okay. So, for this we use a simple idea called the linearity of expectation. Okay. This is an extremely important property of expectations. The idea is that the expectation operator, so this thing, this is a linear operator. What do I mean by linear? That is, if you have f, which is a linear combination, please remember linear combination from our discussion. If its f is a linear combination of two other functions g and h, alpha and beta, let us say, are scalars. So, alpha times g of x plus beta times h of x is f of x, then expectation of f can be written as alpha times expectation of g plus beta times expectation of h. Okay. So, this is an important property, we will just prove it in the next slide. Okay. Also notice that I have used the compact notation here. Instead of writing expectation x tilde p f of x etc., I simply used expectation of f is alpha times E g plus beta times E h. Okay. So, you can apply this, I will prove this shortly, but before that let us simply apply this to our 2 dice case. Remember that in order to find out the expectation of the 2 dice, we actually had to find out first the probability distribution of each of those occurrences, different outcomes, and then we had to do the expectation calculation. Okay. But suppose we notice that the 2 dice are essentially 2 different random variables summing together, one is d1 and one is d2, d1 where d1 is the value that you got out of the first dice and d2 is the value that you got out of the second dice. Okay. So, through our linearity we can write expectation of x is expectation of d1 plus d2, which by linearity is equal to expectation of d1 plus expectation of d2, and we know this already because the expected value from one dice is 3.5, the expected value from the other dice is also 3.5. So, the expectations add up and you can see that this is a remarkably simple calculation. Okay. This is a much simpler calculation compared to actually finding out the overall probability of probability distribution of x. Okay. So, that is the advantage of using linearity of expectations, and this is a very commonly used property. Let me give a very quick proof, I will be doing it just for continuous variables. So, assume that f of x is a multivariate function. This is true not only for univariate, but for multivariate functions, and it is a linear combination of g and h. We want to prove, okay, this is our claim, the expectation of f is alpha E g plus beta E h. So, here is a quick proof. Okay. So, assuming that this is a continuous distribution, you can write E of f as integral of f of x p of x dx. This is of course the definition of expectation. Now, f of x is alpha g plus beta h. Okay. Now, we can split this integral into 2 different integrals. Since alpha is a constant, you can take it out of the integral, alpha does not depend on x. So, alpha times integral g x p x dx plus beta times integral h x p x dx. This of course is the definition of E of g and this is the definition of E of h, and therefore, you end up at the proof that E of f is alpha times E g plus beta times E h. Now, you can also start from the other definition, E is equal to sigma, or E of f is equal to sigma f x p x dx, and since this is also a summation, you can prove discrete also similarly. You can, I suggest that you try this as an exercise. Thank you.